The thing that's really different about quantum mechanics is that it puts information theory front and center. We're comfortable thinking about testing physical theories in new, very physical regimes, much heavier, much hotter, much higher energy. But in quantum mechanics, you also have this option of testing it in different information theoretically interesting directions. There's some classical information emergence that comes from quantum mechanics, and so we want to test quantum mechanics in the very classical information regime, but still quantum. The progress keeps proving quantum mechanics right, and at some point it will break.
Hello, welcome back to the Quantum Foundations podcast. Today I'm joined by Will Zeng, who will be talking about observers in quantum mechanics and some recent work that he's been doing on experiments to test various aspects of observers and the interesting things that these kinds of experiments and ideas can tell us about reality. So, to get started, Will, could you tell us a bit about yourself and what you do?
Sure. Well, now I do two things. So I'm founder and president at Unitary Foundation, which is an open source research nonprofit in quantum technologies. And I'm also a partner at Quantonation, which is a venture capital fund that invests in early stage physics tech and a lot of quantum technologies. And my whole background's been in quantum technologies and advanced computing. Most of my research has been in quantum computer architecture, some quantum foundations, quantum algorithms, that kind of stuff.
Mm-hmm. Great. So that's quite a range of things in the quantum tech space. What is it that led you in particular to do work in quantum foundations or to be thinking about these fundamental aspects of quantum physics?
Yeah, I mean, one of the things that's always really gotten me into quantum information is that you get to do two very different kinds of things at the same time. And it's pretty rare to do them at the same time. So on the one hand, you get to build technologies that could be really impactful. And on the other hand, you're analyzing really fundamental questions about how quantum physics relates to information theory, which is a very deep question. It's kind of like a mind-body question. And so when I first learned about quantum mechanics and then learned about the quantum technology possibilities, the chance to do both those things at the same time really appealed to me. And I feel really lucky that over the last 15 years, I've gotten to do different aspects of both.
Mm-hmm. Cool. And then what is it that led you to end up thinking about these ideas with observers and quantum mechanics? How did you get interested in that?
Yeah, well, I think everybody, when you learn quantum mechanics, should have a big question mark about observers that pops up in the beginning. Mm-hmm. And depending on how you get taught it, the postulates of quantum mechanics are kind of surprising. There's a few that are introduced around, state vectors representing systems in Hilbert spaces, and then they're described with some kind of evolution. And so there's kind of this whole set of rules that describes how the world works, and you can get comfortable with that. And then there's another rule that says when you measure something, use this equation instead. And it says, doesn't tell you when to apply the measurement rule instead of the Schrodinger equation normal rule. You just kind of figure it out as you go along. And so even from it being introduced, this is something that is, it's kind of a tension that's in most textbooks. And I think most people, unless they're told to shut up and calculate, spend a bit of time wondering about why do we have this other rule and how do we know when we apply it? And isn't there some kind of inconsistency there? And a lot of it can boil down to there's these terms in the postulates that just aren't defined. What is a measurement? What is an observer? That's not part of quantum mechanics. We say what a system is. We say how to mathematically model a system. We say how to mathematically model how to put two systems together. We say how to mathematically model how they evolve in time. And then we just have these other kind of ad hoc terms. Mm-hmm. And it's called the measurement problem, which is one of the really big, there's a lot of different subsets of it. It's been around for a long time. And then about 3 or 4 years ago, I started to learn about some new developments that kind of related to it, called these local friendliness inequalities, which we'll talk more about, and got excited about the potential to do some new experiments.
Mm-hmm. Yeah, so there's been this kind of long-standing mystery of how this postulate comes about or how it's defined with these aspects of observers and measurements that aren't well defined. And then more recently, there's actually been progress towards having a way to tackle these questions or to understand more about them.
I mean, the question's been there since the very beginning. And a lot of the times when people talk about how do you interpret quantum mechanics, it's trying to give some kind of epistemological or ontological scaffolding to the measurement problem, or quantum gravity, which is like the other thing we don't understand as a big category yet, and which you just talked about on another podcast. But I think what's motivating for me is that the notion that interpretations just come down to some kind of social or aesthetic choice has always been pretty unsatisfying. Which is not to say I don't have aesthetic views about like which interpretations I like or don't, but the different ways of interpreting quantum mechanics are pretty radically different about how reality is structured. Some of them involve like vast numbers of multiple universes all happening at the same time, which is like a level of ontological baggage that's extremely large. And some of them involve like non-local connections between different parts of the universe all at the same time. They're very different. And so I'm very excited by the chance to do experiments that might shed some light on where quantum mechanics might be wrong, or which interpretation might be right, or just sort of help transcend the paradigm. And the history of experimental quantum mechanics is sort of, maybe 80 years, 100 years of people looking at the math and saying, this is weird and it's hard to understand, so why don't we have a thought experiment that can help clarify it? But we'll never be able to run the thought experiment. And then like 20 years later, 40 years later, we start to actually run it. And so far, quantum mechanics has been right. But that doesn't mean we shouldn't keep trying to find places where it might be wrong. Does that make sense?
Yeah. So this is one of those places where there's a chance it might be wrong.
Yeah, I don't know how to have a prior over it, but like what I like about the local friendliness experiments that we'll talk about is they're very concrete experimental protocols. You do some particular thing in the lab, you measure some numbers, they violate some bound or they don't, and that tells you something about reality. And there's other things like that have happened over the last 100 years in quantum mechanics. And I think those are, they're very practical and concrete, even though they're about pretty abstract questions about the foundations of quantum mechanics.
Yeah, cool. So, could you tell us a bit about what these experiments actually are? How can they tell us approach these questions about the measurement problem?
Yeah, so one of the historical places to start with this version of thinking about the measurement problem starts with Wigner in the 1960s. He introduced this little thought experiment called Wigner's friend. And the setup is there's a Wigner, and he's got his friend. And he puts his friend in a box and seals him up so that he doesn't look inside the box. And it's not a very nice thing to do to your friend, but why not? And so then we take a particle, some quantum system, that's in a superposition. So like imagine it's a photon of light that's like red or blue, one or two different colors, something like that. But in quantum mechanics, you can have superposition of these two things. And so we send that particle in its superposition into the box. So we describe all of that with what are called the unitary postulates of quantum mechanics, which is just like kind of all the normal rules. And then what the friend does inside the box is she measures the system and uses that other rule. So from the person in the box's perspective, they've measured either a red photon or a blue photon, and it's no longer in a superposition. But if we zoom out and we look at Wigner, who's outside of the box, that's all happened inside of a box, and Wigner has no information about the measurement outcome. It's all sealed off. And so the way Wigner should model it is that a photon in a superposition of red and a superposition of blue has gone into the box. The friend has done a measurement, but that's not a measurement for Wigner. That's just that's the unitary evolution of rules. So Wigner sees a superposition between the photon being red and the friend seeing red and writing down red on one side. And on the other side, the photon being blue and the friend writing down that they measured blue. And that's a bit weird because this is, Wigner talking in the 60s, that's a bit weird because from the friend's perspective, there is no superposition. And from Wigner's perspective, there is a superposition. And if you want superpositions, which describe the state of reality, to be objective, to be a real thing with ontological property, then it shouldn't depend on whether you're the friend or you're Wigner. And so that's a bit odd. So that's what questions about that, and then we can go to kind of what's happened recently. And then there's been something that's happened recently. Yeah.
Yeah. So in this standard Wigner's friend setting, we've got this kind of tension where Wigner is applying these kind of unitary rules for quantum mechanics, and then the friend is applying this measurement postulate, and so you've got these different rules being applied in different settings.
Right.
Well, for different people within the same setting somehow.
So this gets to the issue of how we're usually taught quantum mechanics, which is that you're not told when you can apply which rule, and there's no concrete specification. In a lab, we can kind of agree when to do it, broadly speaking, and there are particular experiments where you actually have to be really concrete about where you make this this cutoff of using the measurement classical rules as opposed to the quantum unitary rules. The term for that is the Heisenberg cut, like where you start doing one rule instead of the other. But there's nothing in quantum mechanics that says you have to put it here. We get to choose. So what's happened more recently is starting in I actually don't know when Czasław started thinking about this, but probably the early 2010s. Czasław Bruckner and Renato Renner and a bunch of folks on the theory side started looking at the Wigner's friend thought experiment and came up with some ways. So that thought experiment just raises some questions. How do we make that something you can measure and determine something really concrete about? And the approach is something that Eric Cavalcanti likes to call experimental metaphysics, which is basically asking questions about not just how quantum mechanics acts, but how any possible physical theory needs to behave. So it's not an experiment saying, is one physical theory correct? It's an experiment talking about a meta class of theories, like ruling out different classes of them. And things like this have happened in quantum mechanics in the past. So like the Bell experiments are also experimental metaphysics. And those ones that won the Nobel Prize a couple of years ago, there you make some assumptions about reality, and you find out that quantum mechanics makes predictions that are inconsistent with those assumptions about reality. And those were made in the early part of the 20th century. And then in the later part of the 20th century, in the early 21st century, people started trying to measure and see, does quantum mechanics actually violate those assumptions? And they found that the answers, we're pretty sure it's yes.
So the metaphysics aspect of it is, that it's applying to it's showing something about physics generally, that it has to, one of these assumptions must be dropped rather than quantum specifically. That's kind of the...
There's some subtleties, but yes, the objective of doing the experimental metaphysics is to try and be what's called theory independent, which means you're saying something about any possible theory that you could construct as much as you can, rather than saying something about, is quantum mechanics right or wrong? So there was some work in the late 2010s, and then some initial experiments by Eric Cavalcanti and Howard Wiseman and Nora Tish's lab to do what are called extended Wigner's friend experiments to violate what are called local friendliness inequalities. And so maybe I should unpack that if you want.
What is local friendliness inequalities?
Yeah, so the structure is we're going to make some assumptions about reality that seem pretty reasonable. And then we're going to show that quantum mechanics violates them. And then we're going to say, well, we should check. Basically, that's the setup here. So local friendliness is a conjunction of two different assumptions about reality. At least this is the way I like to describe it. It's an active, moving area of theory, so there's a lot of ways of defining these things. And I want to say, I'm coming at this from sort of I'm kind of like a relatively practical theorist, and so I've been learning a lot. But there's a lot of subtleties, but we'll do kind of the high-level version. So the first assumption is called the absoluteness of observed events. And sort of high level, what that means is if an event happens, then it happens for all observers. So this is different than relativity. So like in relativity showed that depending on what reference frame you're in, different people might disagree about what time something happens at, for example. But they don't disagree about whether or not it happened. If you violate absoluteness of observed events, then you can have things that happen in one frame, but not at all in another frame, let alone at different times. Make sense?
So is there kind of an example where we can imagine what this would mean? So I guess in the standard Wigner's friend setup where you have the friend in the lab and then Wigner on the outside, are there kind of observed events? How does absoluteness kind of apply to thinking about that?
Yeah, so we'll get into that when we look at the extended radius friend experiments. But if absoluteness of observed events is not correct, then there's at least some way to set up little pockets. So actually, Eric calls them Wigner bubbles. These sort of like little bubbles of reality that are separate from other bubbles of reality. So like there's a set of events that happen for people in this Wigner bubble, but not in this other Wigner bubble. And they are inconsistent. So like another way of putting absoluteness of observed events is if you believe in absoluteness of observed events, then you believe that I can describe what's going on with some probability distribution over outcomes where I don't need to condition on which observer I am. Like there's some joint.
Yeah, so it kind of applies to any, whichever observer is being considered will have the same
we'll have the same
set of
distributions.
Outcomes. Yeah.
So that's the first assumption. And it should seem like pretty reasonable.
Yeah.
It's not exactly the same, but like it's sort of along the lines of like, is there some notion of objective reality? The second one is an assumption called local agency. That's a similar one that is used in Bell. It's in the Bell inequalities too. And that basically says we're able to make some variables that are independent from other variables. And the way we usually do this is by making them separated enough in space that there's not enough time for, like the speed of light limit means there's not enough time for the things over here to be influencing the things over here. So it's usually written as like, there's some light cone and like the things that are happening over here don't affect the things over here. But you don't actually need the speed of light to be the limiter. You just need there to be some limiter.
Right, so sense? It's not tied to speed of light.
But the way we practically implement it is usually the speed of light. But the point is you need to be able to say this variable over here was chosen independently of these variables over here. You don't need to be able to do it for all, just you need to like do it for certain ones in these Wigner's friend scenarios to show the violation kind of thing.
Right.
And that's, it's a pretty weak assumption. It should feel pretty weak. There's different interpretations of quantum mechanics that don't believe in local agency. I find them sometimes not easy to grapple with because if you don't have independent variables, then it can be hard to do science.
So
at all.
So what are some examples of ways that you can, that these interpretations might work, not having local agency?
Yeah, so some category of them are called superdeterminist interpretations, where you might imagine that you're free to choose some measurement setting in your experiment. And you prepare the setup one way, you measure A and you get something, you prepare the measure setup, you measure B, you get something else, then you think you can use that to make to do some reasoning about how the system behaves with independent choice of A and B. But if you're a superdeterminist, you can say, well, no, you didn't freely choose to measure A that time. You only chose A that time because, I don't know, there was a solar flare on Alpha Centauri last Tuesday, and that affected the outcome there, so you aren't learning something about some general case. And so you kind of get these like pernicious correlations that could be possible. I mean, there are, that's kind of an aggressive superdeterminist. That definitely doesn't sound reasonable. Other people have other sort of more reasonable superdeterminist, or non-locally agent assumptions. So sort of like the de Broglie-Bohm, like if you have kind of non-locality everywhere, then you can also drop local agency.
Because there's some kind of underlying physical way that these.
Yeah, like at the Big Bang, we were all close and we all got correlated and entangled. And like later, my choices were determined in the past. And so my choice here was connected to my choice somewhere else. But I do think it, at least for me, it's kind of hard to drop that one. It's hard to drop both of them. But a lot of interpretations try to drop one or the other. Like the many worlds interpretation drops absolute observed events. But anyway.
So the sense in which you said it seems to you like difficult to do science or to understand how you do science in a world without local agency, is that because you kind of can't really reason about your measurements anymore. Is that
you can't reason about independent variables. So it just becomes it becomes hard. I might be wrong. I'm trying to learn more about it. I think there's there's a lot of literature. These are subtle. But the thing that I'm excited about with the experiments is that it's not so much like how do I aesthetically choose? Like I was saying, like I want an experiment that tells me local agency is wrong or absolute observed events is wrong or something like that. So anyway, the setup is we're going to assume absolute observed events and we're going to assume local agency, and those two things together we're going to call the assumption of local friendliness. And the assumptions don't say anything about quantum mechanics in particular. They just say, you can have independent variables and events are objective, loosely. And you could have a lot of theories that, like classical mechanics, also obeys those theories, right? Like it does quantum mechanics. I don't know. So then what you can do is make these two assumptions more formal into mathematical statements that apply in certain measurement scenarios. And for this, I think I should probably use the whiteboard. So when we were talking about, I don't know if this is going to be visible. Okay, yeah, cool. So when we were talking about Wigner's friend, we had a box. Actually, I'm gonna say we've got Alice out here, and her friend Charlie is in the box. And what we did is we sent in this qubit or something into the box. So the idea behind the extended Wigner's friend scenarios is you kind of double this, and you have Bob with a friend Debbie, and then we have two entangled qubits, let's say, and we send them into these boxes. Yeah.
So we have an entangled pair of qubits, and then one sent over to Charlie, one to Debbie. And they're both in their own kind of isolated labs. And then Alice and Bob are on the outside, like Wigner was in the original Wigner's friend.
Yeah. And they have to be isolated because, one thing we know is that if the measurement outcome that Charlie sees or Debbie sees leaks to Alice or Bob, then you can't treat it as unitary anymore. Like then we know it's on the, measured side of things. So, the setup here is that every time we make the entangled pair, we send one to Charlie, Charlie measures it, we send one to Debbie, Debbie measures it. That happens every time. And Alice and Bob are going to then have some choices about these are the choices that need to be locally independent. Have some choices that they make about what to do to their friends. And the first thing they could do is they could peek into the box and see the outcome that Charlie got. So at the end of the day, Alice is going to get some bit and Bob's going to get some single bit. And you can generalize it to make it bigger, but in the small example, a qubit goes in, Charlie makes a measurement and gets a classical bit. Alice, if she peeks, looks in and sets her bit to be the same as Charlie's. Symmetric for Bob. Okay, but there's two other options. I'll just call them A and B. So reverse A and B. And so if Alice chooses reverse A, then what goes into this box is a photon that Charlie measures. But instead of Alice opening the box, to her, this is just some entangled quantum system, which means it behaves unitarily with the first set of rules, and those rules are reversible, which means that Alice, in principle, can just undo the measurement that Charlie did.
Mm-hmm.
So it's sort of like the photon comes in. Sorry, I'll draw it slightly differently. So there's a photon and then Charlie, which I'm also going to draw as like a little line. And then Charlie makes a measurement, and what comes out is, and then what Alice can do if she reverses is reverse that measurement, and we're back to two, I need more space. We're back to two separate systems again.
Mm-hmm.
Where in the middle, Charlie's entangled with the photon, and at the end, Charlie's unentangled. And so then if Alice does reverse A, so Alice will reverse the measurement that Charlie did, and then herself measure the now free photon in one of two different bases. So this is the quantum mechanics thing, like in one of two different ways. So it's kind of like Alice will measure either the position of the photon or the momentum of the photon after unentangling Charlie with the photon. It's not exactly those two. You have to be a little more subtle about which bases you choose, but that's kind of the
kind of analogous to measuring two properties like that.
Yeah, and so in both these cases too, Alice has just measured a single quantum bit, and so Alice gets out a single classical bit. So in all cases, Alice gets out some bit, and that we get some Alice bit that's like just some bit, and Bob's going to get some bit too, given Bob's choices about choosing to like peak or reverse A or reverse B. Maybe I'll call this like 1, 2, and 3.
So these A and B are the two possible properties that Alice chooses to measure when she gets her unentangled photon at the end.
Yeah, exactly.
And then Bob can also choose between those.
Exactly, and it's the same basis for the same properties.
Yeah.
And so, if you run this experiment a lot of times, you'll get some set of expectation values for different combinations of choices. So like, if Alice chooses to, so I measured them as one, I put the 1, 2, 3 to make it easier. So if Alice chooses to peak and Bob chooses to do reverse 2, I can run this a lot of times and get some, what the bit Alice gets of A and the bit Bob gets of B is going to be statistical, but you can run it a lot and see what the expectation value for that is. Similarly, for any combination, I can get, Alice 2 and Bob 3, whatever. Mm-hmm. So what you can show, and this is written up really nicely in a paper by Bong et al. And Howard and Eric and Nora, is that you can get a series of, if you make the assumptions of absoluteness of observed events and local agency, then you can put some limits on what those expectation values are allowed to be. And I don't have any of them memorized exactly, but it's something along the lines of, this is not what it exactly is because I don't have space to write it anyway. Okay, so this is just an example, but like the expectation value of some measurement settings plus some expectation of other measurement settings has to be, below some number if you assume local friendliness. And there's different classes of these. And what you then find out if you calculate what numbers you should get for those expectation values using textbook quantum mechanics is you find out that those inequalities are violated. And so one way to interpret that is to say that quantum mechanics says that textbook quantum mechanics is inconsistent with local friendliness, which means, you need to drop either absoluteness of observed events or local friendliness.
And there's there's kind of no obvious one to drop in a sense. But I guess the this type of theorem tells you one of these must be dropped, and then kind of leads you to it of like, okay, now we need to. It kind of forces you to commit to having to drop one of these assumptions.
Yeah. So unfortunately, it would be really great if it told you exactly which one is wrong. But we're not there yet. Maybe we'll figure out how to do that. But at the very least, it tells you you have to drop one of them. And I think previous to that, you could have imagined that, like, well, sometimes when I'm interpreting how quantum mechanics works, I will drop absolute observed events. Like, I'll be a multiverse person. And sometimes when I interpret how it works, I'll be a superdeterminist. And now, at least you know you have to commit.
Yeah.
And so that's pretty new. But all of those, and for some people that's sufficient. They're just like, well, quantum mechanics must be right. Like, I don't believe in local friendliness. Like, we did the textbook math. Quantum mechanics has been right for 100 years. I'm good. But there's some subtleties. And one of those subtleties is that you need Charlie and Debbie to count as observers for this argument to go through. Because you're going to make an argument about whether or not it's okay under the absolute of observed events for there to be like relative realities that happen for Charlie and Debbie.
Yeah, so you need, for this absoluteness of observed events assumption, you need to be able to have observed events happening in these isolated labs.
Yeah, and for those to be observed events, then Charlie and Debbie have to count as observers. So there's been a few experiments. So like in 2020, 2021, in Nora Tischer's lab in the University of Queensland, in Griffiths, they're neighbors and they're rivals in Queensland. Yeah, I know. They ran a version of this experiment where Charlie and Debbie were single photonic qubits. And they saw that these inequalities were violated. So they saw violations of local friendliness. And interestingly enough, they saw that, as the initial fidelity, the purity of the quantum state that was used in the experiment went up, the violations went up. And as you got more noise and were less quantum, the violations went down, which is like sort of the kind of thing you expect. So one way to interpret that is to say, okay, great, look, we're done. We've proven that reality is not locally friendly. No physical theory of reality can be locally friendly. Like, I'm happy. Another way to react to that, and I think a very reasonable way to react to that, is to say, well, I don't really believe that single photons are observers in whatever way observers are observers. I'm not saying I hold that position, but people do react that way, right? Like, there are some people who believe there's something different about you or me as an observer than a photon. And sort of the thing is, when I say there's no definition of an observer, I mean, there isn't one accepted one, except for the fact that everyone agrees that people are.
Yeah, we're like the ultimate observer.
Somehow, that seems to be if you do the survey thing, then that's what people answer on surveys. I don't like that way I want to do experiments that tell me yes or no, but it's good to kind of share the sociology of it. And so, there are different candidates you could have for like what's different between me and a photon that means I'm an observer and it's not. And so it might be interesting I think it's important to run these experiments and see if you get violations for things that are more and more convincingly observers. Does that make sense?
Yeah. So how can you start going about thinking about how an observer is different to a photon, or more convincingly an observer than a photon? What kinds of things can we think about?
Yeah, so there's like a big history of people wondering about this just from a theoretical perspective, but now we need to take those theoretical perspectives and say, like, how can we use them to tell us what to build in a lab? And so good places to start are people say, well, a person is an observer, and so what are the properties of a person that a photon doesn't have? It could have a big mass. It could have just like many degrees of freedom. It could be it could be conscious. It could have some notion of agency. There's like statistical measures of decoherence, which is sort of like something becoming more classical as well. There's a lot of things that you could start to pick. And one way to look at these experiments is as a test bed for different metrics of observer-ness. Or put another way, if you run these local friendliness violations in different regimes, you're like probing quantum mechanics in different regimes of observers. So this is like an analogy to the kind of thing we do in particle physics. So like we test particle physics at like higher and higher energies where we think things are going to happen or be different at, and we make them bigger and bigger and bigger, and we like see if, you know, the rules still apply. This is kind of like that. Like we're looking at quantum mechanics and we're making it bigger and bigger, and we're seeing if the rules still apply. And there's actually a whole tradition of doing this. They call macroscopic quantum superpositions. It's like sort of studying macroscopic quantum mechanics. You know, all the weird things about quantum mechanics that we know are, well, we really believe are there, but we don't see in the everyday world. We try to figure out like, well, what's stopping us from seeing them in the everyday world? And so we make bigger and bigger experiments to test that. And there's a lot of people working on it. But one of the things you can do with a big macroscopic superposition is say, well, does this count as an observer? And then do a local friendliness violation with it, which would sort of like ratchet up the evidence that local friendliness is not how our reality works.
Yeah, so I guess in a kind of similar way to how there's lots of different properties you might want to focus on with an observer, there's different properties you might want to focus on when making a macroscopic superposition of in what sense is it macroscopic, and then whichever kind of one you've used to create a macroscopic superposition, you can then test out that aspect of an observer's property by putting it into a local friendliness.
Yeah. So like if you believe, you know, that at some point, if you believe that local friendliness is real, that the world is locally friendly, which is like not an unreasonable prior to come in with, then you believe that something's wrong about quantum mechanics. And one of the things you might believe is wrong is that like you'll see these violations until you do this experiment with something that actually counts as an observer. And so in that way, you could flip this on its head and make it an observer detector, which is like if you put the thing in the box as a friend, if it sees violations, then it doesn't count as an observer. But if it does, then it's an observer.
Yeah. But to do that, you'd need to have decided your property that counts as an observer to set up.
Well, yeah, not necessarily. I mean, you could just randomly put things in the box and then like sort until. But this is actually kind of hard to do in practice because you want to say, well, did the violations go away for some fundamental reason?
Yeah.
Like because I found some new law of physics that applies to observers like this? Or did it go away for a more prosaic reason, which is like my experiment has noise because it got bigger?
Yeah.
So, one needs to be careful about that. But, you can imagine a program, and this is kind of what we talk about in our most recent paper, of like running bigger and bigger local friendliness violations. So like, and I'm not going to specify the metric. We'll talk about what the metric of bigger should be. But like, you've got a single photon over here. And we've got you over here. And this experiment happened, back in 2020, 2021. What we ran on some quantum computers is an experiment that's like sort of maybe like over here, moving the observer-ness up a little bit, and we've got ideas for moving it like kind of here and here. And you can also think about how to maybe move backwards. So what's something that's like a person but might be easier to put in a box like this? And one of the hard things, it's hard to put something in a box to isolate it, but the really hard thing here is doing that reverse maneuver, where you like unitarily reverse everything that happened, which like from the perspective of the observers might look like, I don't know what it looks like. It's like you're reversing their time locally for them. Is maybe one way to interpret it. So Howard Wiseman and Eric Cavalcanti and Eleanor Riefel kind of had a fun way to think about moving this direction, which is instead of having a person, why don't we simulate a person? So with some kind of like, imagine you can have an AGI, some simulated version of an intelligence. So that's probably a lot of the properties that people have, like this agency or some kind of notion of complexity in processing or something, will also apply to an AGI. But this AGI, we're going to run on a quantum computer.
So artificial general intelligence, that's like, not just like the AIs that we use on ChatGPT or something, but something at the level that's like a human but in a computer kind of thing.
Yeah, this is more like an uploaded human. You can think about it, whatever sci-fi term you want. But an uploaded human that runs on a quantum computer. And the thing that quantum computers can do is do the unitary reversal. And so you can sort of ask, like, how big of a quantum computer do you need in order to fit maybe as many bits as kind of represent the state of your brain, which is kind of the estimate that Eleanor did for this paper. I can't remember exactly the number of like Toffoli gates, but it's I think it's above 10 to the 20. Like it's pretty big. But that might, doing it with an actual person seems really engineeringly hard. This at least, we have, if you imagine a 100-year time scale, sort of sci-fi roadmaps for building a quantum computer that big. So there's kind of different ways we can sort of approach it from one end to the other.
So on this end, it's kind of like, building up from the photon, which is like 1 qubit, to doing it with more and more qubits. And then by the time you get to AGI, you've kind of got so many that it could run this program of being like an observer.
Person,
Good. Sorry. Are there any other kind of points on this scale that you'd kind of think of as like milestones or something that would link to something that we think of as an observer or measurement device or something?
Yeah. So one way to think about it, there's a few other things you could put on here. So one thing you could put on here is maybe something that's like a photo detector, or like, some like macroscopic system in a lab where, we don't, when we're working in practice, we don't actually think that the system becomes classical only when it hits like my eyeballs or the eyeballs of the postdoc in the lab. It's like if I run the experiment and go on holiday and come back, like it wasn't unitarily evolving in a superposition until I came back.
Yeah.
Like we don't really seem to think that that's what's going on. So, like lab devices or something like that. And one can get more quantitative. But an experiment we're running, so these first ones we ran using more qubits on quantum computers. I can talk more about it if you want. We have another experiment that Nora's leading in her lab, which is to use more photons, but in a custom lab setup, because the human eye actually can detect a surprisingly small number of photons. So if instead of a single photon as the friend, we have like hundreds of photons, it doesn't have to be millions or anything. Depending on what studies you look at and how statistical you want to be about the confidence that the human eye detected it, it's sort of arguing that humans can see less than 100, but it's kind of like you have a clicker that says that it's a bias that you saw it or something like that. But if we get up to that scale of like a few hundred photons or 1,000 photons, there's not going to be a human in the box. But in principle, if your eye was there, you would have seen the difference between the outcomes.
Yeah.
And so maybe that's an interesting milestone.
Human distinguishable in a way.
Yeah. So it's sort of like it's an interesting biological question to look up, of like what the most sensitive modality we have as humans is. It might be light. But in any case, we're certainly pretty sensitive to light, and so if you pick light as your like degree of as your physical system, then like human distinguishable actually happens pretty small. But that's the principle that we were trying to get at.
Yeah. Yeah, that's cool. So maybe we can talk a bit about kind of what how you figured out a quantity to actually put on this scale, or to be able to start doing these experiments.
All this is mostly it's not me figuring it out. It's mostly me like reading and seeing like a lot of the recent stuff other people are doing. So I have two kind of favorite 2.5, I'd say, kind of like favorite statistical measures right now for observer-ness. The first one is not one that we use, but it's mass. I still think mass is quite interesting. There are sort of different ways that people have argued about why if the friend has a certain amount of mass and them observing like a red or blue photon causes that mass to like be in one place or another, that will cause there to be a superposition between space-time metrics, which like won't persist because there'll be some kind of collapse due to that. Now, we didn't have an experiment to do that with yet, but I do think larger and larger masses, like it's not an arbitrary quantity that people have that photons don't. Like it starts to connect to these questions around like how does gravity interact with quantum mechanics, and like does gravity suppress large superpositions, and if so, then maybe if a superposition is big enough mass, then you are an observer. That's kind of the high level reasoning there. So I think mass is good. The other ones are sort of more like information theoretic or complexity theoretic. And so Taylor and McCullough from Australia, we did some workshops kind of about this topic, which is like one way of me getting to learn a lot. But we did like a theory workshop, and we did a experimental workshop where we just brought people together to be like, all right, like what's going on here? What are some metrics? And kind of while that was going on, they came and they published this paper where they talk about something that they call branchiness, which we call branch factor because I think it sounds a little nicer. But the notion is that this is hard to do for the general audience, this one, but basically the idea is observers are classical, which means they have regular bit type information, like fixed classical information, as opposed to quantum information. And so you could argue that a system is a good observer if the computational complexity of telling the difference between it being classical information and quantum information is very high.
So you're imagining that like a system like a photon has this kind of is very quantum information.
Well, so there's like, so classical information is, what's property of classical information? Well, it's easy to distinguish. Like you can tell the difference between a 0 and a 1 classically. It's very easy. But it's hard to interfere classical information, which is like, this is like the fundamentally like quantum interference sort of thing that we can do. And so if I give you a system that has like two states, then you can use a computational complexity measure to say how easy is it for me to distinguish those two states from each other, and also how easy is it for me to interfere those states again. Because if you interfere them, then you like needed to keep track of the fact that it was quantum, because you can't interfere classical things. But if it's really hard to interfere and easy to distinguish, then you can basically replace it with classical information.
So there's these two aspects of distinguishability and interference. And the easier it is to distinguish, the more kind of classical
it can't just be that. It has to also be hard to interfere. So you need you need two things. You need to be easy to distinguish and hard to interfere.
To have the kind of classical.
That's what we kind
property.
of argue. We say that if you have that, then we call it high branch factor. The branches comes from this notion of like, branches of specific classical realities emerging from superpositions of quantum ones.
Right.
Yeah.
But if either of those is kind of the other way around, like if it's difficult to distinguish or easy to interfere, then it's kind of quantum.
Yeah. In turn, and they talk about actually in the paper that like good quantum error correcting codes, like things we want to use to make big quantum computers, kind of are the opposite of high branch factor things. Like they're dual to it. Because you're trying to do the opposite. You're trying to like make
to use the full quantumness of the
so like
structure.
you can say it the other way, like so you need to interfere to do the quantum stuff in a quantum computation, and you don't want to be able to distinguish states, because when you distinguish the state on a quantum computer, that's information leaking out, which means it's decohering. So you actually want it. It's like you're making it in a bad box. Like,
Yeah.
so
Yeah.
a good quantum error routine code is kind of the opposite of these things. And so doing
Yeah.
these experiments is like a little bit in tension.
Yeah.
Anyway.
Yeah. Yeah. That's an interesting point because I guess if it's difficult to distinguish, then that means information isn't leaking out. Kind of that's the
Yep.
idea. So there's this branchness or branch factor quality is kind of capturing. It's a way of quantifying kind of this combination of how the bigger this quantity gets, the bigger this combination of being difficult to interfere and easy to distinguish is getting.
Yeah. But there's a lot of, like, I want to be clear, there's like tons of open questions in this thing. Like, branch factor is not exactly canonical in the sense of, like, it's not exactly clear. Like, it's pretty clear how to calculate how it scales. So like complexity scaling kind of things. Like, as the system gets bigger, does the branch factor get bigger as a polynomial? Does it get bigger exponentially? Like that we can calculate. But like, what's the number is not exactly clear because it kind of depends on things sort of like choice of basis and choice of decomposition. And so there's these kind of things in it that like I want it to be an ontological quantity, not something that you have like free choice about how to calculate. Actually, Jess Riedel just put up a paper. Oh gosh, what is the title of it? It's like can we define branches or something like that on the 18th, where he talks a little bit about Taylor and McCullough's paper and also some work by Weingarten. And it kind of gives like a nice sort of view on like what we would want to say about branching. And what we'd want to say is like, give me some physical system and I can just calculate like how well it has branched without needing to make a bunch of choices. That's kind of, and right now we make some choices that are like a little bit unsatisfactory. So there's these asterisks, and another one of these asterisks is that there's some loopholes, and in particular in all the experiments that I'm aware of so far, we haven't really enforced the local agency condition. Because in order to do that, you need to separate the parts of the experiment far enough away from each other that there's not enough time for, light and information from one part to get to the other. So that's called like not closing the signaling loophole. So that's another thing to actually do to like close that loophole. And actually we can build on a lot of technology for that was used to do the Bell inequality violations, because they had the same assumption of local agency, so they had to do the same violation. And so we need to do the same thing. And in order to do that, you can also use some of the new quantum network technologies that people have been developing. So that's another direction to go, is to close that loophole.
Yeah, cool. So it's kind of an application of some of the recent progress in quantum technologies with the networking.
Yeah, all of it is. I mean, sometimes people have this view that like, well, science develops some technology and then hands it over to be commercialized. And like, that's just how it goes. But not really. There's like an interplay where what's happening in quantum tech in particular now is, science is developing technology that's going into industry that has applications in different areas, but then we can use the tech that's developed in industry to make bigger and better experiments. Like we've been running on quantum computers to get bigger and bigger observers. We're going to use quantum networking technologies to do the no signaling stuff. And some of the like really ambitious programs for space-like separations are pretty big. So a couple weeks ago, I was at Helgoland, which is this island in the North Sea with 200, well, not permanently, I was there temporarily with 200 quantum physicists. And we were all there to celebrate the 100-year anniversary of quantum mechanics. Because in 1925, Heisenberg went there to escape hay fever and ended up writing down a lot of the matrix mechanics that would become quantum mechanics while there. So there wasn't like one birthday of quantum mechanics. It kind of evolved with a bunch of different people at a bunch of different times. But that's as good a mark as any. And this island has like 1,400 people on it. It's 3 miles across. And so we were like a good cohort.
Yeah, just taking over.
Taking over and all there. And a lot of people were talking about, different frontier experiments in quantum mechanics. And that's something that I really liked. Sometimes these break into disciplines, but, you had really great people in the field get up and say, well, here's how I've been thinking on the measurement problem, or here's what I'm doing on quantum gravity, or here's my collapse model, or here's my interpretation of quantum mechanics. Like, like we're still kind of grappling with, despite the fact that it's so darn accurate in calculating so many things, we're grappling with a lot of the same questions that have been around for 100 years. But there are differences now than there were 100 years ago, and a lot of them come down to what technology we have that's available. And so to loop back to this like signaling loophole, Jean Wei Pan, a great Chinese quantum physicist, was talking about, someone brought it up as a question too, but like, do you want to do one of these Bell inequality violations between the moon and the Earth? Because that's enough space-like separation that there's enough time that you could actually have a human on the moon or a human on Earth register the outcome. So it's a little bit related to this with Bell inequalities, but that's a pretty big experiment. It relates to ideas of making quantum communications network in space, but also doing big foundational quantum experiments. And maybe just like another anecdote that I was really impressed by at this, of just like how far our technology has come, is Xu Junyi, who's at NIST in Colorado, gave a really wonderful talk about the progress in clocks. And if there's anything we as humans can measure really well, it's time. And they're starting to design and build clocks that can measure time accurately down to 10 to the minus 19, 10 to the minus 20, which is wild. And just to give you a sense of how wild that is, time dilation happens as you change how far away from the Earth you are, right? So, you move and time will slow down or speed up as you get closer and slow down. And if you have an accurate clock, then if you lift it up, you'll see that drift, right? And these clocks that they're making now are so accurate that they can see the drift that happens due to the change in the Earth's gravitational field over the width of a human hair.
Wow. That is very crazy.
It's really crazy, and pretty new. And what's there's two remarkable things about that. Like, one is it's amazing that we've been able to develop that technology, and I'm really excited about what new technologies like that. I mean, you have to use quantum mechanics to make a clock that's that good.
Yeah.
It's a fundamental quantum clock. I'm excited for what those kind of technologies will help us to experiment on to answer some of these long-standing questions about what comes after quantum mechanics or how quantum mechanics works.
Yeah.
So that's one reaction. The other reaction is quantum mechanics has been so right that we've had to keep making. Why hasn't it broke? Why didn't it break at 10 to the 15 to the minus 15? Like, we have to really keep pushing it.
Yeah.
But we will.
Yeah, it's interesting when. Yeah, I guess it's an example of a regime where you're getting these different types of theories coming together. Well, you kind of have the consequences of special relativity and of quantum mechanics. You're really sensitive to both of them, and it's cool when you're in that setting.
Yeah, I mean, if we want to do things like these quantum gravity experiments where you detect a superposition of times, or superposition of space-time metrics or something, you need to be able to measure time really, really accurately. And so some of the next step things I've talked about already. So we want to use bigger quantum computers. We want to separate the quantum computers. We want to do custom photonic experiments where the observer is big enough that in principle it's human distinguishable. And then there's great work that's going on, like in Vienna with Markus Aspelmeyer and Marcus Arndt and Yiwen Chu at ETH Zurich, where they're building macroscopic superpositions in different forms. And mostly to study quantum gravity is what they've mostly been thinking about. But I want to repurpose their systems, and I've been talking about it, to count as observers in these kind of local friendliness scenarios and see what we get.
Yeah, cool. Yeah, it's cool to kind of take things that are being developed, I guess, with a kind of different foundations motivated purpose, but then using those developments to then find another cool conclusion from it.
That's the thing. Yeah, I think some people think like physics has sort of slowed down in terms of the fundamental new things about reality that we've learned maybe in the last 30 years, something like that. I think it's kind of maybe true. I think the limiter is we just needed technology to catch up.
Yeah.
It's my hypothesis, is that like we need technology to catch up to get good enough that like we can see. It's not that quantum mechanics is the final theory like that. Like, like I don't think that's it. And it's not that from here on all the things we'll do are make aesthetic arguments around how to interpret it, and like the theory will tell us. Like, and there will never be again experiments that guide us in new ways. Like that's not the case. And these kind of experiments are a lot cheaper than $100 billion particle accelerator. And I don't know exactly what we're going to find, but if we move forward a little bit on the experiment, and that causes us to need to clarify the theory, which is kind of part of what's going on here. Now that we're actually saying, okay, let's run experiments where we care about the metric of if it's an observer, then it starts to become a little more practical around like what you, like how you define and calculate these things.
Yeah. So do you kind of generally feel like we're at a stage where the tech has caught up to the level that it can now inform back into the...
Well, it's always been doing it.
Yeah.
Like it's just like I think so far theory has come up with weird experiments. The tech has caught up, and it's proven quantum mechanics right. And like but I don't think that's not why we haven't learned new things, because we're not making progress. It's just the progress keeps proving quantum mechanics right, and at some point it will break.
Yeah.
So there's like a lot of dynamism, but it's
more new things is when it breaks.
Yeah. And there's like quite a few ideas, and there's really like a lot still that we don't understand a ton about. One thing I'll do like a shout out to that I'm reading now is, so Zurek has a new book about decoherence, which just came out, where he sort of, I've only read the first few chapters, but he's sort of like redoing quantum mechanics without this weird ad hoc measurement postulate, which is kind of what this promise of this decoherence theory that he's been working on for decades does, and I'm pretty interested to see. Another view is like, that it's taken us this long. Like, there's no new experiment that kind of led to that. It's more just like it is more just like thinking about the fundamental. Like, even though the quantum mechanics is the same, we can think about it in a new way, and the experiments informed that, even though we didn't do an experiment that like clearly violated quantum mechanics. I'm not sure if that made sense. Like, I guess what I'm saying is experiment can inform theory even when it isn't like violating the theory directly. I think that's what I'm saying.
Yeah. Yeah, I've been planning to read that book as well. I saw it.
I just started.
Yeah. Yeah. Cool. So, so to kind of recap a bit this story with the observers and local friendliness. We kind of started with this measurement problem of you've got two types of evolution, kind of normal quantum mechanics, then this measurement postulate, which involves measurements and observers, and it's not clear how to define them. There's a kind of vagueness in that postulate.
Yeah, so Chaslov says it often in like a pretty good way, which is like if you didn't have all of the social conditioning and you just saw the atoms in a laboratory, how would you know which parts are the system and which parts are the measurement apparatus? Like, how do you know? And I think that's kind of where that question is.
Yeah, that brings to the fore the question of like, where that line is of distinguishing the two. And that kind of question appears in this Wigner's friend thought experiment of imagining an observer does a measurement, someone is outside that lab, they use one description, the observer that did the measurement uses the other description, and so you've got these two descriptions going on at the same time, which is kind of strange. But then you've got this local friendliness inequalities are kind of turning that into something that you can that's kind of an actual violation of something rather than just
it makes them quantitative. It makes it operational, measurable, and quantitative. That's the
And in that setting, you've got a similar thing to Wigner's friend, but now there's 4 observers, 2 in the labs. They share an entangled pair of particles, and then you have the 2 outside the lab, and then the ones outside have the option to, the ones inside do a measurement of their entangled particle. The ones outside have the option to reverse that measurement or not, and then they'll measure the particle themselves if they reverse the observer's measurement. So then you've got these sets of different possible combinations that you can get of their measurement outcomes. And then the local friendliness inequalities are showing that if you violate the inequalities, then in this setting of this kind of experiment, then you'd have to drop one of 2 kind of quite core intuitive seeming assumptions about reality. One of them being absoluteness of observed events and the other being local agency. And the different interpretations of quantum mechanics you can kind of map onto choosing one of these to drop, but the theorem forces you to kind of drop one of them.
Or you introduce like a collapse model that says that when you have an observer, those violations are going to go away. That's a consistent position. I'm not saying it's my position, but...
So in that case, instead of dropping one of those 2 assumptions, it's kind of saying that the dynamics of quantum theory are different, which is why you're changing quantum mechanics.
Like you're changing quantum mechanics to say like at some point, like it's to say when you're supposed to apply the measurement rule, basically. I don't really know what, if any of these outcomes is going to happen. I mean, I guess I have some views, but like what I want to do is be an empiricist and say like, let's run experiments that give us evidence in some direction. And I'm really interested in experiments that tell us which of those 2 assumptions might be right or not, or are the ways to think about them.
So there's different ways to explain what is happening if they're violated, but it's kind of you have to make a decision on something if they're violated. And then so the theory says that they're violated, but then there's the question of actually demonstrating that, like we've done with Bell inequalities, showing that there's no local hidden variable models. You want to show that we can kind of rule out that these assumptions can all hold in our reality.
But even there, I mean, there's still some loopholes in the Bell stuff. Like in the Bell inequalities, you make an assumption about where the cut is. It's actually very specifically in the 2015, like the major paper, they say we put the Heisenberg, because you need to put the cut somewhere, because that's what determines if there's enough space-like separation for the time to affect it, and for there to be enough time for one side to affect the other side. And they pretty explicitly say, like, we put it at the measurement, I think they put it at the measurement. I mean, they know they put it somewhere in the measurement detector. Like, they don't put it at the grad student. So, there's still some details there, at the very least.
Yeah. So there's still loopholes in Bell.
I mean, it's all. I think it's aspirational to do the experimental metaphysics truly theory independently and truly without any loopholes.
Yeah.
But it's still evidence gathering.
And I guess you can always consider how you'll get closer to making it more theory independent or more. You can keep getting rid of the loopholes kind of
exactly.
through further iterations. So in this program of research, you want to actually implement these experiments testing the assumptions. It's been done with kind of the observers being single photons, and it all checks out, like, yes, we have to drop one of these assumptions.
Without the space, with the loophole still there, but without space separation. And then we did it on quantum computers with up to 17 qubits making up the friend. We're scaling that up too with some new error detection stuff. But again, the same loophole. And then we want to do the large number of photons, which would be like in principle human distinguishable. And then we want to start using some of these kind of other macroscopic superposition things that people have made. We've made these mechanical resonators that like are in superposition. Like they're really like lots of atoms, but they're vibrating back and forth physically. So it's a lot of atoms moving, but they're not moving a very large distance. And so, you know, that isn't so useful for quantum gravity because the distance matters if you want to detect the difference between the two spacetimes. But maybe for us it's fine because all we care about is sort of the mass.
Yeah, because it has... Right, so is that a kind of nice direction for the mass version of the experiment that you were saying you're quite
I've been pretty impressed by some of the experiments Yuan Chu's group has done at ETH with mechanical resonators, and if we can couple them to photons, maybe there could be something there.
Yeah, cool. Yeah, so that's the stage where things are right now is kind of pushing towards those milestones as the next levels of observer to test in this setting.
And as we go, we'll get better. I mean, we have these kind of proto-metrics for what an observer might be, but we're also understanding better the theory of how to like calculate and define what these branches are. Because I think one of the things that's really different about quantum mechanics compared to any other physical theory is that it puts information theory front and center. Like information is part of the physics. Like the physics, it's physics of information as much as it's a physics of like ontological things that we poke at, you know, like the information itself has physical effects. And so like I was saying earlier, we're comfortable thinking about testing physical theories in new, like very physical regimes, like much heavier, like in black holes, or like, you know, much heavier, much hotter, much higher energy. You know, like that all makes sense. Like we think a physical theory works in the energies we interact with. Let's test it at really big energies, or test it at really small energies, something like that. But in quantum mechanics, you also have this option of testing it in like different information theoretically interesting directions. And I kind of think that's what this is. Like we're testing it, there's some information, there's some like classical information emergence that comes from quantum mechanics. And so we want to test quantum mechanics in like the very classical information regime, but still quantum.
Yeah, with those regimes being the type of thing that you get in these branches.
But we're still working out like how to calculate some of these things.
Yeah, because there's not a kind of obvious physical property that it attaches to in the same way as, say, mass is like very well-defined physical property. It's kind of trying to capture this property of the branches, which it's not clear yet what the kind of intrinsic...
Yeah, it's at the border of basically, it's at the border of what we can operationally and informationally say. It's like the border of saying, if you say something's computationally complex, does that mean it's physically not allowed? Like, maybe, kind of? Like, that's part of the question.
Yeah. Cool. So you've mentioned that you're kind of quite motivated by having experiments that can tell us something interesting and not necessarily making aesthetic choices about things. But do you have a general kind of feeling of what you'd expect to see from these experiments, or what you think they're telling us about reality, or do you prefer not to
I think
put your judgment on that?
Well, I think as we run, I think the program of running local friendliness experiments at more and more significant observer scales, I think is going to tell us stuff that's relevant for the measurement problem. And if we're lucky, it'll tell us something about like the accuracy of quantum mechanics. But I don't know what the answer is exactly going to be. I mean, I sort of think the worst case is kind of like what happened with the Higgs, where like we'll just keep running this, and eventually we'll run it with a person in the box.
Yeah.
And we'll say like, well,
and it all works.
now local friendliness is definitely not true. But even in trying to do that, we'll come up with some amazing technology. And if you can put people in boxes like this, then you can like create not just virtual reality on a computer, like actual, like Wigner bubbles are real. Like there are like you've made a technology that makes like personal universes. So
Yeah.
anyway, even that's like the worst case, in the most worst case in the sense of like maybe the most boring,
Yeah.
but it still ends up with like a pretty radical bit of technology. I don't know how long it'll take that we can do that, but maybe it's not buildable. But.
Yeah. Yeah. So the most boring scenario is that we end up with multiverses that we can each or bubbles that we can all that we can create and engineer.
Yeah, I think, and there's some people. Eric has a view from the Wigner bubble paper where he talks a little bit about this and how different interpretations kind of relate to it. Some good sci-fi probably. still waiting to be written.
Yeah. Cool.
Thanks, Maria.
Yeah. I just think we've covered everything. Is there anything?
Last thing I want to say is all the software for running these experiments on quantum computers is all open source at the Unitary Foundation GitHub. All the papers always will be open source and open access. So, if you want to run them, you could run these on IBM quantum computers. Some of them are for free. We're always looking for people to do stuff.
Yeah, great. So, people can be an observer being part of the chain.
Right, yeah, exactly.
In some sense.
It only the wave function only collapses when you make the git commit with the measurement results into the repo.
Yeah.
That's probably the theory of physics.
Yeah, cool. So I can put some links to that or the papers in the video description so people can go and try things out for themselves or read more about these things and progress in this direction. So thanks for coming on to the podcast. And I think there's it'll be exciting to see how these experiments develop into these different milestones and directions that you've mentioned, and see if we can, see if quantum mechanics keeps getting proved right indefinitely, or
that's the real. I think maybe I'm speaking only for myself, but I think a lot of us maybe we just want to see what comes after quantum mechanics, because quantum mechanics was so weird and amazing when you first learned about it. You're like, I want to have that experience again.
Yeah.
Because I don't think almost the weirdest thing is if the thing that came after quantum mechanics was not weird.
Yeah.
Like it somehow became like very simple.
Yeah.
And very intuitive, which would also be amazing. So I hope we can. I was encouraged by the Helgoland conference. There's like a lot of new technology, a lot of people thinking about this stuff, and so I enjoyed learning from them. And thank you for having me on. These podcasts you do are great to expose more people to a lot of that work.
Yeah, thanks. And speaking of the other podcasts, we do have another few episodes relating to Wigner's friend ideas. So if you find it interesting, you can have a look at those. They came up in a conversation with Nick Omrod about causation, and we talked about the multiverse and Everettian quantum mechanics, where it's also kind of relevant in an episode with Sam Kuipers. And then with Andrea Di Biagio, we talked about this local friendliness theorem in kind of some mathematical detail, and also the different interpretations like cubism and relational quantum mechanics and many worlds and how they relate to these assumptions. So they're all on YouTube if you want more detail. And thanks, Will, and see you next time.